overhead portion that feeds the underground is still effective. The biggest benefit to underground is that aesthetically, the appearance, the line's invisible. People don't want to see how their service is being fed. Also, the underground that's not directly affected by the wildlife and vegetation contact on the line. Another benefit is it's concealed and it's not as accessible to be a public safety concern. In the event of an outage, it may be difficult for the troubleshooter to find the problem. Drawback to both overhead and underground construction, the poles get hit, but also ground mounted equipment is going to get hit. We hear a lot more that the poles are hit, but that's probably because there's more installed in the underground. The underground's in place near a roadway, they're going to be hit probably just as often, and they're probably going to take longer to repair. The process to convert overhead distribution to underground is difficult for several reasons. You've got to think about all the services to the homes and businesses in that span. All of that's got to be converted underground. It's hard to find locations for those because we're also dealing with sidewalks, bike paths, and underground utilities. Ultimately, for an overhead to underground distribution conversion, we need to consider the cost and if it would be worth it to city utilities and our customers.
Okay, that was a short but sweet video. What are the benefits, guys? What he said was the benefit of overhead versus underground.
It's accessible to be repaired. You can see the repair visually, like you can visibly see it, as opposed to kind of guessing what's going on.
Right. I mean, and I can tell you guys, just from my experience, when I worked over in Sumter, one of our, of course, it's probably small for your area, the Myrtle Beach area, but we had a subdivision that had like 12 underground dips on it, and it fed off of 2 different feeders. And when you had trouble in there, you might have been in there an hour. It might have been an easy fix. You might have been there all day or all night trying to figure out, where that, span of bad cable was, or if it was a bad transformer or whatever. But if it was a small storm, and just like you saw in the video with the tree limb laying across the primary, you got a bunch of calls in on outage, you could probably have that limb removed and back on within an hour, depending on the size of it. But you're right. What you can see is a big benefit.
Yeah, you get assistance from the public.
Yeah.
Well, right.
I can't tell you how many times I've had somebody follow me around town or somewhere just to stop me and say, hey, I saw a big ball of fire come off a pole on such and such a street. You go right to it. I mean, that just saves you an awesome amount of time. So what you can see overhead is a time saver, and underground, you just really don't know, you can't see underground, so you really don't know. You have to troubleshoot, isolate cable. I mean, that's very time consuming. So good answers. Now, drawbacks. What did they say some of the drawbacks were from?
Wildlife.
Oh,
Wildlife. It's more accessible to wildlife, and they'll mess up.
yes. Squirrels. That's probably our number one, trouble causer out there in the industry. I've seen squirrels get on it and blow them to pieces, eyes bugged out. I seen them get on the line. When I got there, I see them laying on the ground smoking, walk up to the pole. One of them actually got up and just waddled away. I'm sure he died later, but yeah, squirrels. I've even seen cranes, those big gray looking cranes get into the line. Those egrets, anything that can fly, crawl, snakes get up there, cats get up there. Just all kind of wildlife gets up there. And too, like I told some of you guys yesterday, we were looking at the shotgun stick, and I said, we were talking about it, and I said, a shotgun stick is great to pull a snake out of a transformer. They like the warmth, especially in the wintertime, and they'll curl up in the bottom of one of those transformers where it's dry, and they are great for grabbing those snakes and snatching them out.
I have a question.
So don't think that just because it's, underground, there's no animals. I mean, raccoons, possums, I've seen just about any kind of animal that can crawl out the woods be inside of a transformer or some kind of underground enclosure.
What's your question, Paul?
I didn't have one.
I thought somebody said they had a question.
No, sir, not me.
Okay.
That's
Uh,
Dave. Is my damn.
So, and the last thing I'm gonna ask for, forget Professor Shoemaker to interject in is, so what's the main reason why everything is not converted to underground?
Cost.
Money. That's pretty much the driving factor for most things in the world today is money. You know, if the company's got enough money, if there's a lot of times now, the government have put grants out there and the utilities can go for it and they can use that grant money to, you know, go from overhead to underground.
Yeah.
And there can, like in the picture, let me back it up to where the car hit the car. I mean, they do run over transformers. I've seen this many times where they actually run over the transformer and knock it off the pad. Why, you can see back in the back where the primary cable is just everywhere on the ground. And I like the other picture better, that one right there. And that's what sometimes guys are gonna ask you to take a pole out to the job site with your car. So that's what you're gonna have to do. But that happens so many times, especially in, I would say, the Myrtle Beach area, the Raleigh area, those big areas that are putting everything in underground. You'll see that, just like you saw in the other picture where the cars run into poles, they run into this stuff too frequently. And it's a mess. And this is some very old cable. It doesn't have that outer jacket on the primary. It's just got the concentric. So I'm assuming that with that happen, they probably replaced all that cable with the new jacketed cable. So, I mean, it has its drawbacks, underground versus overhead. But every area still has overhead, but a lot of it is being, you know, transitioned into underground. Professor Shoemaker.
Yeah, I mean, you've touched on, you know, everything that I want to speak about. Safety wise, I mean, you look at this picture right here and it's kind of amazing. I've seen plenty of wrecks and cars run over underground equipment like this. And the safety aspect of this too is, remember that that tip that's on the elbow that's sticking out and all this is what they call a dead front enclosure. Thank you. All of this can remain energized.
Mm-hmm.
Even after you run over it. And I know it looks like a wiry mess going out down there, but you got to treat this just like you would treat an overhead line that fell on a vehicle or a vehicle was on it. Is considered energized until you've gone to the points to switch it and get it open and consider it dead.
Yep.
So yeah, it has been, sometimes I think it's, you know, wow, that thing looks like it's been sheared off at the, and then you go down there and you put a tick tracer or a tester down there and you know, one or two of the modules are still hot. And you're thinking to yourself, and you know, some of the companies that are wreckers that go out here, or the person steps out of the car, you know, it's kind of sketchy, guys. So,
Yeah.
you know, just be safe when you get into situations like this. The other part, you know, when we're talking to overhead to underground, we did the computation there in Myrtle Beach when Myrtle Beach wanted to convert all of the boulevard overhead to underground, and you're looking at 4 times the cost.
Yeah.
So if it costs $100,000 to build it overhead, it's going to cost right around $400,000 to build it underground, and a conversion from overhead to underground is going to be about $300,000 because you're going to get some money back on the material that you took out. Now, also included there, North Myrtle Beach, Surfside Beach, and just recently Pawleys Island went into what they call a franchise project for the conversion. Whereas if the municipality, will say Myrtle Beach, taxes there, and this is typically hotel tax, has a hotel tax and pays for half of the conversion, the utility will pay for the other half. Because, you know, really in the long run, if you convert, especially on the boulevard, if you convert from overhead to underground, you have a hurricane come through or a hard storm come off the ocean, you're not going to have to respond to trouble calls like you did before. So they're what they call franchise projects to be able to compensate for that money. Oh, and overhead. Oh my goodness.
Huh.
I mean, if you can think about it in nature, it's happened out there. Bears I've seen up on transformers, foxes, squirrels. We had a real bad problem in Lakewood Campground, and we couldn't quite figure it out, that geese were flying into the three-phase line. And their wingspan, they were getting wrapped up in the three-phase out there. And we were going like day after day after day for outages on that line until we finally, put a real big spread. We had to spread out the line a long way because they were, how they pitch in and land.
Oh, yeah.
They were going right through that line and getting tangled up in the line. So overhead and underground, I mean, there's benefits and drawbacks to both, but
Right.
in the long run, I think, underground is the best.
Yep.
It's just expensive. Any questions about anything that we've discussed out there?
Just a quick one. The underground picture where it was all destroyed by that car, what would be the easiest to replace? A fallen pole that was damaged by a storm, or one of those?
Oh, it's going to be a pole.
Always easiest.
Yeah, a pole. You're going to jerk if it's a busted pole and out of the ground. You're going to set a new pole in the ground, and everything's going to be pretty much exposed. You're going to be sitting on that one right there,
Yeah.
probably with a couple crews for the full day.
Yeah.
I mean, yeah, you got a pole sitting right there.
Yeah, so all that
Yeah.
wires on the ground and everything.
Everything right there. Well, everything's exposed and just really ready to be put back, Paul. You put that new pole in the ground, you hang a new transformer, you just pull everything back to the pole. If you need to do splicing, you need to do that, and you just reconnect. Go to the underground one, Robbie.
Okay. The mess.
Yeah. This one, you're going to have to take. Let me get this real quick. Yes, sir. Good, good. No, sir, we're not. No, on the desk is fine. Okay. I appreciate it, buddy. All right, yeah, I appreciate it. Yeah. All right, bud. Bye. Sorry about that, guys. Sorry about that interruption. So what you're going to have to do here is you're going to have to remove all these terminations that are existing on it. Get all new conductor out here. Now, there's really no splicing to this, and you cannot run a splice through conduit.
Right.
So you're gonna have to take all these terminations off. You're gonna have to re-pull, and from what I'm seeing down there inside the enclosure, that's 1, 2, 3, 4,
It's a lot.
possibly 5 or 6 conduits
Yeah.
in there. You have to re-pull all that conductor, re-terminate all that conductor. Robbie, I'm thinking 2 to 3 times
Yeah.
the amount of time and labor to get that one repaired than it would be to replace a pole.
Yeah. Yeah, that's pretty nasty.
And your pole is sitting there and all of your wires exposed. Depending on this conductor wire, you might have to get pulling equipment.
Yeah.
They call it an underdog. We'll talk about an underdog later. It's just a pain.
Huh.
Okay, anything else?
Okay.
Okay. I had a little bit to go along with that one too, because I wanted to show this video on my side. And it's something to know and remember when you're out there. Let's see, which video was it? All right. Theater mode. I'm going to share my screen. This is a guy replacing a fuse on an underground dip and getting ready to close it. You got that?
Got it.
So he's replaced it and he's getting ready to close. pretty decent explosion, you know, and everything on an underground dip. And this is, you know, I had an engineer tell me, and there's some different things that are going on as far as, you know, breaker settings. We'll talk about that later. That overhead faults or overhead problems, something that might be on the line, are typically 75% of the time temporary. What do I mean like that? A squirrel gets on a line and gets shocked and blows a fuse, it usually falls away. Or a tree limb causes a fault, or an animal. Typically when that happens on overhead, you know, it kind of clears itself. That's what we call it. It clears itself. So all you have to do is, well, yeah, I found a squirrel by the pole. All you have to do is go back and replace a fuse. Underground's a little bit different, gentlemen. When you go into underground, the engineer was telling me, those are 90% of the time permanent faults. What do I mean by permanent fault?
Like you gotta replace the whole wire or something?
Yeah, something is wrong somewhere and it hasn't cleared itself. It hasn't fallen away. And, you know, transformers, we know that transformers are very, very reliable and they're very, very sturdy. So, you know, most of the time it's primary cable. And if you have a fault in underground primary cable, it doesn't go away. It stays there. So, you know, I kind of question, and I don't know what's going on in this situation. I question why you're closing a fuse on an underground cable right here. And it's something we want to go into a little bit further. What did we talk about yesterday to be able to test our cable? What can we do to test our cable to see if it's got a fault or not on it? What do we use? Remember the two old guys with the sticks? What did they use?
Could you repeat the question?
Remember the two old guys in the video yesterday when they had the two sticks?
Yeah.
Yeah, what did they use to test the underground cable with? High pot adapter. You can high pot adapt across the switch. That's the point I want to try to get across to you. They did it on a connection inside an enclosure. All you need to do is replace those connectors that were at the end of the sticks with hooks. Isolate the underground going to the first transformer. That's where my mouse is going. And take one stick here, high pot, and one stick here, high pot, and you can high pot the first span. So I want to make you guys aware of that. They were doing it from a point on inside an enclosure. You can high pot the first span. So obviously, did they do that here?
No.
No. Now, in the olden days, this was, and this picture does look kind of old, even though it does look like a new stick. That's old framing. Look at that insulator.
Yeah.
Yeah. In the old days, before you had high pot sticks and all that cool equipment that we've got now, this was the typical means of finding out if you had bad spans. So you would open in the first transformer, close a fuse. If the fuse held, you'd open the next transformer and close, open the next and close until you blew a fuse. Well, they got away from that. One is you're blinking the lights every time you blow a fuse on the line. And two is every time you put a fault on underground primary conductor, it is stressing it. So that's why we went to the high pot method. And there is actually another method we're getting ready to go into in just a moment. But do remember that overhead faults typically clear themselves. That does not mean you do not have to patrol it. If I have a fuse, and we'll just use this one for example, and this fuse is going down this line, you have to take your vehicle or go on foot and walk down and physically view the entire line. If you don't find anything, refuse it and re-energize it. Underground is typically permanent. So do remember that. You're obviously got a fault somewhere that you need to find and isolate. Does that make sense?
Yes.
Okay. All right. So that's that video right there. So let's go ahead and get into the second method. One, and this is, going to be one of your test questions. There are two methods to finding underground fault, primary faults in spans. One is what's the first one we've learned about? You just said it, Cole Kennedy.
iPod,
High potty. I go from switch to underground primary, and then I would do what they call leapfrogging. I go to the first transformer test, second transformer test, third transformer test, on and on and on and on until I find the faulted span. The other method here, and this is, I wouldn't say too modern. Let me get to it. I got some pictures. Nope. Nope. Is what they call an underground fault indicator. So method 1, high potting. Method 2 is an underground fault indicator. What you're seeing here is a 3 elbows that are going into a transformer right here. They have a device that you can strap around the primary conductor. You see it down here in the lower right-hand side. I'm taking my mouse around it. That goes to a cable that goes and mounts on the outside of the transformer, and they put theirs on the side. We typically put ours right down here in front so you could drive by and see it. So if you have a fault on the cable, what is the reading?
red.
That's an F in the red.
There's an F in there. Okay, there's an F in that one. So that means beyond this point, there was a fault. And I'm going to get out Microsoft Paint in here in just a moment because it's easier to explain that way.
Is that reading on the outside of that unit?
Yes, you see how this arrow is pointing right down here to the side?
Awesome.
So you can, we really didn't like them on the side right here. We wanted to put them right in front so you could drive by.
Yeah.
Yeah, so you can mount them anywhere you want to, but we put them down here at the lower part of the transformer so you can walk by or drive by and see the F shining in this picture right here. So fault indicators are the second method to determine in span which span is faulted. So let me go over here. Here's one, and there are different types. We did move to the fiber optic type.
Yeah.
Eventually, but this is one that straps around the primary conductor but has no remote indicator. You have to open the door and actually look at the indicator, and this one is showing fault. If it was clear, this flag would turn around, you'd see a white flag, and I don't know why they put this in there with an N in it. The N is not neutral, that's for sure.
No.
The N is not new. I don't know what they put the N in it for, but showing white, your cable is clear. You've got good cable. Okay, so let me go back to this other picture here. Question?
So we had high potting and underground fault indicator.
Underground fault indicators, and we're getting ready to discuss here in a moment how they work.
What did you just
Well,
say? You
and
said,
that was it.
go ahead.
Go ahead, Paul.
Ms. Schumich, you said fault indicator determines in span. And what I
Yeah,
missed-
we're getting to that in just a moment.
I want to know what it is, what you just said.
We're getting that in just a moment.
Okay.
I'm going to show you on Microsoft Paint. It's just easier to show that way. First, let's go back to what's going on here. How is this able to determine that I saw a fault? Let me get back to this. Where was the picture I just had? No. Well, here we go. Okay, you'll notice, I'll use this one. It's going to be okay. You'll notice right here, you see how the fault indicator is strapped around and coupled to the primary conductor right here? Around each primary conductor.
Mm-hmm.
Now, it's reading, and a lot of people assume it's reading amperage around the conductor. And once that amperage gets too high from a fault, it trips the flag. That is not the case. If I put an amp meter on every single primary conductor that I've got out there to get fault indication, I'd be spending a ton of money. There is, though, something that happens with all conductors when they have a high amperage load on them, or even a low amperage load. What is given off by a conductor when it has current on it? We actually talked about it when we were doing locates in 60 hertz yesterday.
Magnetic field.
It gives off a magnetic field, exactly. All that's inside these indicators right here is an opposite or opposed magnet. Okay, once the magnetic field on the conductor gets too high, it trips the indicator. So the indicator is not, current is an effect. The magnetic field is what's being measured. Then really, essentially, all they have inside these things is an opposite magnet. They've got a north-south magnet sitting in this thing, and once the magnetic field gets too high, it trips the indicator. No battery is required. Nothing's required in this. That's the nice thing about it. You don't have to replace anything because all I have in here is a magnet. So these things can be sitting on the cable forever. These can be sitting on the cable forever. So question's going to be, what trips a fault indicator? I'll wait.
High voltage or too high?
All right.
Magnetic field.
The magnetic field from high current. Okay. The magnetic field from high current. That's what makes the fault indicator trip. Also, and you've got to watch out for the indicator. They have become a lot better. It takes a certain amount of current for it to go back to neutral. Current must exist on the cable for it to reset. Now, obviously, if this trips from a fault and you fix the problem, what do you want this flag to do?
Go down.
Go down. So there's a minimum amount of current that's required to make it go back to normal. Last time I left, it was 3 amps, which is not hard to do at all. So 3 amps is required to reset it back to neutral. And then you're just carrying on with business until there's another fault. All right. So Paul.
Yes, sir.
Let's get to how they work, buddy.
So you said high current from magnetic field is what trips the fault indicator, correct?
High current creates a magnetic field.
Okay.
That's an attribute. The magnetic field trips the fault indicator.
All right. Thank you.
You're welcome. No problem. All right, so I'm gonna have to unshare so I can switch screens to get a draw screen here. Oh no, no, no. Okay. All right, so I'm going to stop share here and start another share on the opposite screen. Share screen, paint, share. Okay, so I'm just going to draw like a single phase line scenario from a dip pole right here. Can you all see that paint screen?
It's on.
Okay, great, thank you. Size, this. So I'm going to start with a dip pole. I'm going to draw a fuse here. Come down the dip pole. This is with underground wire. Go to the first transformer. Go to the second transformer. Just going to add about 3 in the line here. Go to the third transformer. And here's my little single phase enclosure. I'm just going to stop. All right, which side do we feed into the transformer with? Left or right?
Left.
Go in the left, out the right. In left, out right. In left, out right. Coming to here, stopping. And this is the symbol for dead end. All right. Now, it depends on your company and what they want to do. It's kind of a toss-up, 50-50 toss-up, where I put my fault indicator. All right, typically what we'd like to do, especially if we were coming off a fuse right here, is we would put our fault indicator on this cable. That's the outbound on every single transformer. Okay.
Mhm.
The fuse, now remember this, the fuse is your first indicator. It's a fault indicator in itself. If you have a blown fuse, that is your first fault indicator. So it lets you know right away, I need to isolate the first span and test the first span. All right. Here's what the nice, that's with high pot adapters. Here's the nice thing about fault indicators. Okay. The indicator here is red. The indicator here is red. The indicator here is white. The faulted span is always between the red and white indicator. I can't say it any more simple. Professor V?
Yep, easy.
That makes sense.
It does. Now, we'll go into a little bit more depth of why. All right, say the fault, and we're doing it in this scenario. The fault occurs right here, okay? It's returning, remember, neutral's back this way. This is where we're grounded at, all the way back through the back of the line. Did fault current go through this indicator? Fault is here.
Yes.
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 That's why it's turned red. Did fault indicator go through this indicator? I mean, fault current.
Yes.
Yes, that's why it's red. Did fault current go through this indicator?
No.
No, because the fault happened but prior to it. That's why it's white. Okay. Fault is between red and white indicators. Now, Professor V,
Yes.
as with everything in the world, is this right 100% of the time?
No, it's not.
Nothing ever is. Okay. It's a very good and reliable indicator that is your bad span. But we always went through the process of going ahead. Now, if we had, and I'll show you here just a minute, another drawing. If we had a red and white indicator, we'd come to this one and we'd put our high pots on it and high pot that span just to make sure.
Right.
Right? And high potting would just make sure that you had the bad span and your indicators did work correctly. Now, I've drawn a simple 1, 2, 3 transformer span. You're going to get in subdivisions in some projects that have 20, 25 transformers in a span.
Right.
So you can see if I'm able to drive by this one, come to this one, up, found it in a 25 transformer span, well, you're saving a ton of time.
Mm-hmm.
Okay. All right. So I'm going to go one more thing here. And I'm going to say this is transformer 2 and transformer. That's transformer 2 and transformer 3 that we saw before. So I'm just going to draw those two. Okay. In the left, out the right. In the left, out the right. Where do I have my fault indicators installed?
On the outgoing leg.
On the outbound cable. Now, this is something to remember. Even though transformers are very reliable, this is something to take into consideration also. This one was red. This one was white. I'm going to ask this question to put a little thought into it here. And remember, this is the conductor going up to here. What is the fault indicator in this span looking at? What is it monitoring? I don't see if my crossbar is going through there. What is it monitoring?
The out in the left one and the in on the right one.
You're right. And what else? You're almost there.
Current flow.
No, it's not monitoring current flow. It's going to monitor, and see the magnetic field change. But I want pieces of equipment. What is it? looking at, and you did have the cable, correct?
Yeah.
Okay, let me change the colors here. So you said the cable from this point on, not the cable going into here. Let me change colors. Let me get rid of that. Not that cable. And watch the blue line. It is monitoring all of this cable that's going through this span up to here, and what else?
Through the transformer?
Through the transformer to where?
The indicator.
The next fault indicator. So remember this, guys, it's not only monitoring the cable, it's monitoring the transformer too. And in some rare cases, I only saw a few of it, lineman came down and they've got a red and a white indicator, and their assumption was, I've got a bad span of cable in here. They isolated it and tried to re-energize from the opposite side. We'll talk about loop re-energization later on. And the transformer was actually bad, so they blew another fuse on this side over here. All right, there really is no method. We did have a piece of equipment that we were able to carry around and test three-phase transformers with. We only had one, and it was very, very expensive. You're not going to typically, unless Professor V, you've seen them happen regularly. We did not. You're not going to test transformers.
Right.
A transformer tester is very expensive to test windings and everything inside a transformer. I just want to give you guys the heads up and knowledge that not only is the indicator looking at the conductor itself that's going through the span, it is also monitoring the whole transformer itself. And you may have the possibility of a bad transformer. Rare, but it has happened before.
Question real quick, Mr. Shoemaker.
Yes, sir.
If you had a dip pole in this picture right here on the left side of that transformer there, and you had to switch on the pole, so that would technically monitor from the dip pole through that transformer to that fault indicator.
Mm-hmm.
So that would be the same concept.
Yeah, think of this. I mean, it's not your typical. It's not one that you're not going to find any company that's going to put a fault indicator, and they do hang on the line. You can put them on wire. They're not going to put a fault indicator right here at the bottom of the switch. The fuse is the indicator.
Yes, sir. And that's what I was saying. If it'll still monitor that first transformer.
That is correct, because the fuse. You're exactly correct. There's no more I can say. If this fuse is blown, well, let's do this. Let's do this. Hold on. Watch this. Don't say. Black. All right. Fuse. Dip pole. First transformer. In the left, out the right. Fuse is blown. The first indicator is white. There you go. My indicator's right here. Where do you think the fault's at?
Between the pole and the indicator.
There you go. There you go. Does that help?
Yes, sir.
Yeah, helping the situation. Yeah, there you go. That is your first indicator. Okay. This one's white. Well, I've determined its first span, maybe a minute possibility is the transformer, but I've determined its first span because I have a white indicator right off the bat. No fault currents pass through it. Make sense?
Yes, sir.
Okay. All right. That was a little bit to chew on this morning. What time are we holding there, Professor V? Sir?
9:43.
9:43. Well, let's say it's 9:45. Let's take about 10 and we'll be back at 9:55.
Cool.
Okay, it's back time, so we'll go ahead and get restarted. What I've drawn on here on the board for you guys is a situation. These are certain situations to look out for when you're using fault indicators and in the fault indicator process. Now, you've noticed I've drawn in a bunch of transformers here. And I have a dip at one end and a dip at the other end. And we talked about this when we were out in the field. I've got a normal open point out here in the field. So a couple of things to look out for. Now, typically when you go out and you start at brand new build in a subdivision, you're going to install a lot of transformers, and you're going to have the homes aren't going to be built yet. So you're going to have a situation where you've got a lot of transformers out in the field with fault indicators in them, going from transformer to transformer to transformer. And especially when you get down towards the end here, you're going to run into this situation where we talked about before. How many amps does it take to reset an indicator? Do you remember what we said just a little while ago? 3 amps. Okay. Now, when you install them in the field, and there's an easy way to do this, most of the fault indicators that come in the box, the ones you're going to install, are already faulted. And they're meant to come that way for you to reset them. Whenever you get a shipment of indicators that come in a box, and usually they come 25 to a box, they also include a reset magnet. All you have to do is wave the magnet across the indicator, and it's going to put it to neutral. All right. So you're going to install all of these after you set them to neutral. But because you don't have 3 amps on the line continuously, you may have a fault anywhere. If there is not enough load, especially down here towards the end, because the load is really tapering off towards the end, you might not have enough load that if a fault occurs, if it's less than 3 amps, if a fault occurs, it won't register. So that's just a heads up on that part. Just be aware that if you drive into a subdivision and you've had a blown fuse here, the fault indicators may not work correctly if there was not enough load on the line. So you may have a red and a red and a red down here, and all of a sudden it turns white, white, white down on these. If there's not enough load on the line, and it is kind of hard, you can't tell that because your power is out now, you might get a false reading between the red and the white indicator. That's one scenario. Now, if you drive into a subdivision that's built, it's been there for a while, you can pretty much rely on those indicators to be right. Another scenario, and this is what some companies do, Professor V, jump in on this one, is that what they'll do is they'll come into a subdivision, dip pole, transformer, and I'm just going to draw 5 for this situation. Transformer, and out is they'll put a fault indicator here at the first one, and they'll skip a transformer. Skip fault indicator here. So if I have a red indication here, I skip this transformer, and I've got a white indicator here. It does isolate my area into this span, this transformer, and this span to here. What do I need to do from here to here?
High pot.
High pot. That is correct. I have to high pot this span, and I have to high pot this span before I can restore. Now, that's just the cost savings on fault indicators. That's all that is. I know we did that in some instances when we first started installing them. Then fault indicator prices came down, and we went transformer to transformer.
Yeah,
So
we never did that. No, we always put them in every transformer.
we always put them in it. Well, Duke's got all that money. So.
Yeah, they're local.
So just to make you aware. Okay, so that's just 2 scenarios to look out for in situations where you're using fault indicators. Are they a great tool? Absolutely. And I'm getting ready to show you a video here of another type. They're a great tool to use, but don't rely on them 100%.
No, I wouldn't.
Okay. Always test. And that's what we always did in spans.
Yeah.
So
Quick question real quick.
yes, sir.
It's just to say if you skip the transformer like you did right there, you can always go back and install one in that one that you didn't put it in, correct?
You can, but you're going to have to reclose a fuse and possibly blow it again. That is it's a great idea. So I'm going to install one here, install one here, install one here, and then I'm going to reclose a fuse. It's definitely going to blow because I haven't isolated anything in this area yet. All right, it will narrow it down to either this span or this span. It will narrow your search, but you had to reblow a fuse to do it. Okay. Now I'm totally honest with you. Before fault indicators and phasing sticks existed, that's what we did. I don't know if you're ever going to run into a company again that does it.
Uh-uh.
Okay, here's my transformers. What we would do is we'd have the blown fuse here. That's our first indication of we got bad cable. We would come to the first transformer and pull one elbow off. Close the fuse. If the fuse blew, then we knew it was in the first span. Right? If the fuse held, we go to this next transformer, pull an elbow off, put this one back on. If it blew the fuse, you see where I'm headed?
Uh-huh.
We knew it was in this span.
Yes, sir.
Okay. All right. Every time that you do that, you're putting fault current down your primary conductor. And every time that you put fault current on a conductor, especially underground conductor, it degrades it.
Yeah.
So the company got far away from that. And it shortens the lifespan of the conductor. So the company got away from that and they got into the phase and sticks and fault indicator method. But before they existed, that was our typical mode of operation, was blowing fuses to find the faulted span.
And
Well-
the crew I was with in Kingstree is a smaller crew. We had phasing sticks, but we didn't have the high pot adapters. So we blew a lot of fuses. We usually designate the low man on the crew to be the gunny and let him see the fireworks.
Yeah. And what it was is one or two guys would be on a radio doing this part, and you'd have a guy in a bucket truck with a long stick, or a guy on the ground with an extension stick with a pocket full of 65 amp fuses.
Yep.
Ba-bam, ba-bam, ba-bam. And I've seen nights that we've done it, 4 or 5 fuses get blown out here.
Yeah.
There is also an effect, and we'll get into that when we get into electrical power systems, that every time you close the fuse, you're blinking everybody's lights that's on that entire circuit. We'll talk about that later. And that's just a pain in the butt to the rest of your customers.
Yep.
Okay. All right. So that's, we've gone over high pots. We've gone over fault indicators. One last part of the fault indicator part, I'm going to show you, it's a different type of fault indicator, but I will show you the installation method. So let me stop this share and get you on a new share screen. Okay, let me get this square over here. And we're going to screen 1. Let me know if you can see screen 1 there.
Got it.
Okay. Now, just a quickie here, because this is a little bit different. The assembly, that blue assembly that you see right there, is pretty much the same assembly, but these are more modern, a little bit more pricey. Is they actually have a fiber optic cable that goes into the indicator, and this mounts on the outside of the transformer. And what happens if you have a fault on the conductor, this will flash a red light. Now these are great. We've used them before. These are fantastic to use at night.
Yep.
Because you're just driving down the road looking at flashing lights. And so you get to you're gonna have a red flashing light, and in the next span it's not going to be flashing. That's going to tell you which span it's in. But that's the difference in this fault indicator. Now, the drawback of this one is it's battery powered. Every time you have a fault on the conductor, you got to have a battery in here to flash the light that comes down here, and they do have a lifetime. The ones we were using had a 10-year lifetime. Of course, that's can be extended a little bit if you don't have any faults on your cable. The light's never going to flash.
Right.
Right. But if you have faults on your cable, it's going to shorten that 10-year period also, and you have to go back and change out indicators. So that's a little bit of a drawback to it.
Hello, my name is Eugene Weaver, and I'm a product engineer with Schweitzer Engineering Labs, Fault Indicator and Sensor Division. Today I'm going to show you how easy it is to install the Underground Auto Ranger faulted circuit indicator with fiber optic display on an underground cable. This phase sensor can be used as a single phase sensor with local LED indication, or it can be used with a remote fiber lead that mounts to the side of a pad mount enclosure.
Okay. So you don't really need to have, but if you're going to have a fiber optic emitting indicator, you might as well go ahead and get the cabling and the light that sticks outside the transformer. You don't have to have, if you want to open the lid and see the little red flashing light here, you can. But I think this extra piece of equipment right here was an extra $5, $7. Go ahead and get that and mount it on your transformer.
This remote fiber optic display allows you to easily troubleshoot for faults in the field from outside the enclosure. So I'm here in the field with an Underground Auto Ranger with fiber optic display, and I'm going to show you how to install the faulted circuit indicator and the fiber optic display. So let me start by sitting this down and I'll show you how to install the display. First, you'll have to punch a hole in the side of the enclosure.
Okay. Professor V, you could probably get your experience on this. We started ordering all of our pad mounted equipment, switch gears, transformers, 3-phase enclosures, and single phase transformers with the punch out already in it.
Right.
Okay. Some companies do not. You're going to have to drill that hole.
Yeah.
Did you get the transformers that were pre-punched?
It seems kind of funny when the fault indicators changed, that's when they would actually change the configuration on the transformer themselves. So yeah.
Okay.
Yeah, they did various ones.
And it's as simple as taking out 2 bolts, taking the cover plate off and putting your indicator in.
Right.
Then you'll disassemble the display, insert it into the hole, and then reassemble the display head.
I don't really quite get why they do this. Every indicator that we put on a transformer, we put on the front of it.
Yeah.
That's 2 that we've seen on the side. If you're driving down the street and you want to sit in your pickup and it's 29 degrees outside and snowing and raining or whatever, it sure is nice to just drive by it.
Yeah.
It's important that when you're doing this, that your equipment is de-energized, because you do have to reach inside of the enclosure to install it. So I'm going to now take the display lens and attach it to the faulted circuit indicator. It snaps right into place. Then I'll open the core slightly. I can now attach the fault indicator to my hot stick tool. Now for this installation, we're going to use 2 hot stick tools, and I'll position the sensor.
Wow, I never really paid attention to it. Do you see the stick that he's got in his left hand?
Mm-hmm.
That's an illegal stick. That stick is way too short.
Mm-hmm.
Up to the cable, reach around with my other tool, and open the core, positioning it around the cable, and then locking it into place back over the core. I can now remove the hot stick tool from the product, and I've installed the product onto the cable. So now you've seen how easy it is to install the Underground Auto Ranger with fiber optic display on an underground cable. You can use this sensor today to locate faults on your system and improve reliability on your circuits.
Okay, so we're going to go back here and we need to discuss this a little bit. as far as the installation was concerned, that's the proper method of doing it. Of course, if you're working in a brand new transformer that's de-energized, it's a new install, you won't have to use sticks.
Yeah.
You'll just be able to put that on by hand. But I want to get back to this part right here. Okay, I want you to pay attention closely. Do you see what's wrapped around the primary conductor here and going up to the transformer? What are those two wires right there?
Copper.
Is it ground? Is it neutral?
Ground.
Yeah, it's a grounded neutral, and he's got the fault indicator over the top of it. Now he's only taking 2 strands, and you'll do that to go up to the elbow itself. This one on the left-hand side, there's an attachment point right here at the bottom to be able to make sure you've got the outside of the elbow grounded, which is general practice. That is normal practice. All right. How does a fault indicator work? Let's go step back to that again. What is it measuring?
Magnetic field.
The electromagnetic field from fault current. So if a fault travels through the cable in either direction, either this direction or this direction, where is it traveling to? Now I say direction of cable. Where's the fault eventually going? Is it phase to phase or phase to ground?
Phase to ground.
Phase to ground. So really what he's got in this situation where it's sitting right here, and we did not do this practice, is if I have fault current going from the phase into ground, he's actually canceling what the fault indicator is meant to do. Fault current is going to travel one direction, then it's going to travel the other direction going into ground, and it's going to cancel itself. So you're not going to get a true reading off the fault indicator. And I'll go here to paint in just a moment to show you what's going on. Our typical practice is if you needed to have the elbow grounded up here at the top with these 2 strands, is to take and make a loop around the fault indicator and then go up to the elbow. That was our general practice. So no grounds were going to be under the indicator measurement, just the primary conductor itself. So that was our practice. Professor V?
He timed out, I believe.
You timed out? Okay, no problem.
Timed out.
I think he just texted me too. Yep, internet out. Okay, so this in our standards was not a viable installation. No grounds were supposed to be under this at all. There is a way that you can install this with grounds underneath it, and I'll show you in the paint screen. So let me stop this share. And go to a new share. Can you all see that old drawing that I've got right there?
Yep.
Thank you. Okay. The other method of doing an installation. So I'll do the first one that they got over here. Here's my primary cable. All right, they've got the jacket down here and they got grounds coming down. It's tied into the transformer down here at the bottom. Then they've got their strands that go up to the elbow. We would take the strand, either 1 or 2 strands, and make a loop, and then make the connection up here, and the fault indicator would go on. That's one legal way of doing it. The other is, and some companies want it to be this way, is here's my primary cable. All right, here's my elbow connection right here at the top, and here's the grounds way up here. And they're coming down outside the cable. All right, the thing to remember here is the grounds inside the cable are going up in this direction, and when they come out of the top and go to earth ground, They're going down, so they're going this direction. If you put the fault indicator over both, it will still read. Why? It's got to do with this direction. Why would the fault indicator still work? Anybody? Am I still online?
Yeah.
Okay.
Yeah.
Okay. Any guesses?
Fault to ground.
Right, the fault to ground is going to occur, but what's happening with my neutral that's going up the conductor and back out of the conductor? So let's go over here. I'm just going to draw two arrows. Up the conductor, down the conductor. I've got 30, let's go a high number, it's fault current. I got 1,000 amps going one direction, and I got 1,000 amps going in another direction. What's going to happen with that 1,000 amps if they're going two opposite directions?
Cancel out.
They're going to cancel each other out. Current flow going this direction and current flow going this direction, because they're equal in a fault situation, it's just going to cancel. It's actually going to turn into zero because I've changed directions. But have I done anything with the inside inner core of the cable? What direction is it going? Only one. So will the fault indicator work?
Yes.
It will. If my neutral conductor is going in and back out, and I have the fault indicator over both of them, right here in this area, it will read nothing off the neutral. It canceled itself, but it still will read the measurement of the core conductor inside, okay? That magnetic field will still be emitted and captured by the fault indicator. So that is a legal installation. Now, some companies, and this is the way they want to do it, they want to have that neutral covering all of the conductor that they have. This is the elbow that goes on. So they have better protection around the conductor all the way to the top. Leaving this exposed in this area does not give good neutral protection around the conductor. So it just depends on your organization of where you're going to be installing it at and what they do. The problem it will occur is when you do this. We use a piece of primary cable, and I've seen the guys do this before. And they take the ground all the way to the top. This is my elbow connection right in here. Then they come out with grounds, and this is what they'll do. I kind of drew that wrong. Let me undo that. They'll come out with their grounds like this. And they'll twist them all together. And then they'll go down to the ground rod with it. They'll slap the indicator on right here. What's the problem? What direction is ground going? How many different directions? Up only, right? The fault indicator is not capturing it going back out because it's not under the fault indicator. Which way is fault current going?
Down.
Down. So guess what? If you have 1,000 amps going to ground from a fault and the 1,000 amps coming out of the elbow headed to ground, it won't do anything. It actually cancels itself out. And the fault indicator thinks everything's okay. So that doesn't work. So you have to use either one of the two methods that I've shown before. Now, if you come up to a transformer, is it installed in this fashion, and you've had a blown fuse and a fault, the fault indicator is not working. And it's not from the fault of the indicator. It's from the fault of the installer. Any questions?
So you should install it to where it goes from the top right there back into the wire, correct?
Let me jump over to the other screen. That YouTube screen, because we will be able to use that picture right there. Stand by. And you can follow my mouse. All right, you see that video picture that I've got right there?
Yeah.
Yes, sir.
Okay, good deal. All right, so practice here. And what we would do is in our install, we would not even put those two strands underneath. Now you're going to have to ground the elbow. It's got a static ground on it. We would take those two strands, follow my mouse, and go around the outside and then ground the elbow. Now all I am measuring is the magnetic field. The current fault current that goes through is the magnetic field of the core of the wire. That is a good thing. If I go down here to the lower left,
Gotcha. So
now
yeah.
stand by a second, then I'll let you go with your question. If you look down here at the lower
Yep,
left,
gotcha.
there's a neutral wire coming up inside the jacket and then back out. If I put my fault indicator over all of it, it will work because I have the neutral conductors going in one direction and out the other. That's called neutral canceling. It will still work. Does that make sense now? And go with your question if you've got one.
Yeah, it makes sense now. I got you.
Okay, good deal. Good deal. All right, any other questions concerning fault indicators?
I think everybody else is
Okay.
asleep.
Huh? More than likely.
Yeah.
All right. Just as a heads up to let you know out there, we started using them pretty regularly. And in case you see them in the field, even if you see one now, they got smart and they did overhead fault indicators also. So you can actually go out on line sections that are, extraordinarily long, or you want to say you've got a line section that goes deep into the woods off a main feeder line, you can install fault indicators on overhead conductor also. And obviously anything beyond the point of the fault indicator, you're going to get a red flashing light.
You see that much around here with that?
Yeah, in fact, when we get ready to do in the next course, when we do our substation walkthrough, you'll actually see them on some conductor out there. And I'll tell you the purpose of it too, is because you're going from overhead to underground, back overhead. In that situation, it gives you a good indication of whether the overhead has got a problem or the underground, because now you've got an isolation point of, identification point of where it's at going bad. Now, the technology has really, really grown on these things. Some of these things will actually tell you how many times the line has faulted. You see 3 red lights in there?
It's faulted 3 times.
It's faulted 3 times. Some of them will do 2. Some of them actually have radios in them. So a radio can contact SCADA via your dispatch center, and the dispatcher can call you. Yeah, we've got a fault indication at pole number 4, 5, 6, 7, 8, and you can just drive right to it. So the technology has come up a lot as far as fault indicators are concerned. Here you see some down here at the bottom. They actually put the phasing letters on them. So I did want to let you know they are in overhead also. Okay. It's about 10:30. Did Professor V make it back? Nope, he didn't. It's 10:26. Let's take another 10.
I don't think so.
Okay. We'll take another 10 minutes here at 10:26. So it's 10:20. We'll say 10:30. and we'll see you guys at 10:40. Let's take another break. I just went into Google and I typed in underground primary cable, and there's many different pictures for it, but a lot of them do come up with the actual parts of the underground primary cable. We'll discuss these here real quick. Of course, there's the center conductor. That's the aluminum conductor in the core in the middle. The conductor shield. Really, the shield goes around the middle core area. One, to keep it compact, and two, is just another shield area for it not to get punctured into. Now, they've got it in red. There's different types of insulation that you can have around a conductor. I'm not worried about the EPR part. That is the type that they're using here. But just as long as you use insulation is your next part, then you have an insulation shield. So you've got a conductor shield that goes around, insulation, then you got an insulation shield that goes around, that's shielding the insulation, the protector for it. Then a copper wire concentric neutral. Now, does anybody know what concentric means? Because we're going to go over two types of ground that go around a conductor. Concentric. Hold on one second. You should have a new share screen there.
Yes, sir.
Okay. Concentric, when they say concentric neutral, and I'm going to draw the conductor facing down the conductor, so that the conductor core is here. When they say concentric, is that the ground wires, and you'll see me draw them and then I'll go red here. The ground wires are going around the outside, and they're evenly spaced around the conductor. Now, of course, I'm drawing them from freehand. That's what concentric is. Evenly spaced conductors around the full diameter of the conductor cable. That's concentric. Okay, and it is the neutral wire, so concentric neutral. All right. Stop share screen, that one. Share. All right. You got the new screen back?
Yes, sir.
Okay,
Yep.
Thank you very much. All right, so your concentric neutral, and then the PVC jacket. Now you need to look out here. It's the assumption that this outer jacket here is insulated. Is it?
Yes.
It's not. Sorry to say.
Oh.
It's just a protective jacket that goes around the neutrals. One, so the neutrals don't corrode as easily in high acidic soil. And two is, sometimes you're going to push a shovel into it, or something's going to dig into it, not with great force. And you got some protection going on here. Okay. It is not to be considered to be an insulated covering on the conductor. So inside a transformer, if you're moving elbows around, and remember inside the single phase pad mount transformer, I'll probably bring up a picture here in just a moment. If you're moving conductor around inside a transformer and this makes contact with one of the secondary lugs, consider it as you're going to be making contact from neutral to 120 volts, and it will make a pretty good explosion right there. So make sure you maintain clearances from this PVC jacket to the secondary bars and anything else that's inside the transformer. Hold on one second. NSFR-MER. Single phase. Okay, let's go to some images here. We'll try to find one with some conductor in it. Here's a good example. Now, when you're constructing your transformer, and you notice the ones, the single phase transformers that we had out there in the field, you're going to want to try to loop just a little bit of extra cable down here in the bottom. And you'll notice right here, this is covered in this area. But sometimes you'll see the wire come up and it'll make a loop and then come into the transformer like this. The same thing on the bottom. You want to give a little bit of extra. I mean, failure points are obviously going to be inside the elbow. And if the elbow fails, all you have to do is pull that little bit of slack back up and reinstall a new elbow. If this, in this area, which is covered by the PVC jacket, makes contact with the secondary bar, that is not insulated. So you would get a large flash right there. Just make sure that you understand that that outer jacket is not insulated.
So those loops you're talking about, whenever I was working on boats, we'd call them like service loops. So if you do have an issue, you got the extra wire there.
Yes. Let me see if I can find another. You know, and this is kind of old. You don't want to, oops, sorry about that. You don't want to put a massive amount of loop in there. Let's see if I get a little bit bigger in this. But you want to put some, and this is not what they call a box pad. So there's no space underneath. This is coming directly out of the ground. You don't really need too much, but if you're able to get like 6 or 8 inches of extra wire looped up in the bottom, if you have a failure in the elbow, do remember, you don't need to cut the entire elbow off. The failure usually happens at the connection point in here or in the connection point in the transformer. You're going to take this assembly apart, pull it off, cut the bad spot out, and if you notice here, you're only going to need about 2 inches to put a new assembly on. So, I mean, that is one, much quicker, and two, a huge cost savings because you have to repull all this conductor again. That's a lot of money. Let me see if I can get back to any more. Here's one more. I think this would be a good example. Yeah, that's a great example right there. That's probably more applicable to what you're going to see here. Now, he doesn't have the box pad like we had before, where you're able to put more looping cable in the bottom of it. But he does. The installer did. You see this big old loop that he's got curled over in it?
Yeah.
You're right. You're gonna do the same with the other phase that's outbound. It doesn't have the same phase outbound. But I can guarantee you, gentlemen, this is jacketed. Once you pull this off, it's going to want to spring back this direction. Okay. And once this makes contact with any of the secondary bars, that is a phase to ground fault, even with the jacket on the outside of it. Back to what we were talking about before, he has got a lot of extra cable here to be able to re-terminate if he needs to. So that's good information right there. Okay. All right, so it's 10:51 now. There's one little more part, I don't say little, one more part I'm going to go through, and that's about the presentations. We have made a walkthrough of the underground yard to show you all the major equipment. So it's time to go ahead and start working on your presentations, and they will be due Friday at 4:30 p.m. I'm going to go through a demonstration of a presentation for you. There he is. Boss man's back. So let me see, I've got 5,000 tabs going on over here. All right, here we go. Now, not to say that this one's 100% correct, but I'll talk my way through it and talk your way through it. So what he has got here is, of course, his introduction page, underground distribution, and who it was by. I don't know if anybody knows Kent Gibbs. All right, his first slide here is the dip pole. Now, a dip pole takes overhead feeder lines or tap lines and connects them to underground conductors that are placed in conduit and lead underground. Now, I spoke with all of you through the course of the week. Typically, it's not this kind of photo, is it? What picture did you guys take out there at the field?
The one over there right by the underground construction.
Right. And was that fused?
Yeah.
Yes.
Yeah.
Yes. Yes. Fused from overhead to underground, fused is 99% of the time a dip pole. That is the feed going from overhead to underground. This is a feeder switch. If you'll notice, this is not fused.
It's bladed,
So
ain't it?
So what?
It's got the blades on it, like you was
Right,
telling us about.
you're 100% correct, and that's the blade. It is open, but that is
Yeah.
the blade right there. So this could be used as either a dip pole or a riser pole. I want you guys to use that fused picture because that is a dip pole exclusively. All right, riser pole. Now he can get away with the picture this time because this is a feeder circuit. The opposite of a dip pole is a riser pole that has underground feeders coming up through conduit and make the connection to overhead feeder line. The description is kind of decent. Let me go back one. Dip pole takes overhead lines and the feed direction is to underground. That's the description I like to hear. Feed direction is down underground. I'm dipping down. Riser pole is the feed direction is from underground to where?
Overhead.
Feed direction is from underground to overhead. That is a riser pole. Pad mount switchgear. A pad mount switchgear is used as a switching point for feeders, 100% correct, and a fuse point for any taps and protects from any faults and isolates them if present. Very good description. All right, it's a switching point for feeders and it has taps, and those taps are fused. So you have isolation in case you have bad underground. That's a very good one. Good picture too. Three-phase enclosure serves as a junction for three-phase primary conductors so they can be sent in different directions. All right, pretty good description. If you want to add a little bit to that, which I probably would, uses all three phases, A, B, and C. But as far as its purpose, good on the purpose. And his picture matches up, that's fine. A little bit different on the module configuration that you see right in here, but that's okay. Different modules are made for different enclosures. Single phase enclosure. So he kind of skipped around a little bit. I'm not too overly concerned if you skip, because like I told you before, when you first stepped out in the field, I could have all kinds of different types of configurations as far as what equipment I'm using, just as long as you capture all. Similar to a three-phase enclosure, but only has a connection for a single phase conductor and is also used for a junction. Do you guys think that's a good description? It's similar to three-phase, but he gets away with it right here. Has a connection for a single phase conductor and is also used, but only has a connection for a one-phase conductor and is also used as a junction. So I'm okay with that. Now, I would have probably found a little bit better picture. He did draw a line here. I probably would have found a little bit better picture, and you guys have pictures on your phones now, and not included the three-phase enclosure. Three-phase pad mount transformer connects to three-phase underground primary conductor and transforms primary voltage into secondary voltage for four underground three-phase secondary voltages. Good description, got four twice, but that is what a three-phase transformer does. If you want to add a little bit extra here, by the picture that he has right here, it looks a little bit different from ours, but this is what Professor Vermeulen was talking about yesterday. Has three phases in and three phases out. Single phase pad mount transformer. Same as the three-phase transformer in transforming voltages, but instead of three primary and secondary connections, there's only one primary and one secondary connection. I'm not 100% on board with that. How many connections are there in a single phase transformer for primary?
Two.
Two. one in, one out. And I would describe it as such. Okay, one phase in, same phase out.
Mhm.
And it transforms for secondary single phase voltages, not three phase. So that description is just a little bit off. Secondary enclosures, a junction for secondary conductor to be tapped off to different consumers. That's a pretty good description. I probably would have added there to top it off. What does it have inside? What are the connectors called inside? Are they watertight?
Yeah.
Junctions.
Whoever said yeah. When I said, are they watertight? And they said, yeah, well, guess what the connectors are called? Watertight connectors.
Tight connectors.
Oh,
There you go. Okay. How many do I need?
2. Well, no, you need 3.
There you
Three.
go. Excellent. Neutral, 120, 120. Excellent.
Yeah.
Very good. So I probably would have added that in the description also. Well, guess what? You got it on a different slide. A watertight connector is used to connect the underground secondary conductors to the underground service conductors for different consumers. He got it. And then the meter. The underground service leads into the meter base of the structure, and the meter is used to read the amount of energy the structure is consumed, so the utility company can bill the customers. Guys, that's it. Did he include all the pieces?
Mm-hmm.
He did.
Yeah.
Did pretty good on these on the description also. Okay, so are there any questions there?
Is that going to be on D2L?
Yes, we're going to have the Dropbox open for you guys to drop that into D2L.
Is this PowerPoint going to be on D2L or no?
No.
Tenfold.
Okay. This is being recorded though. You'll be able to reference back to it. And once again, it's due Friday.
Gotcha.
Okay. All right. So any other questions? It's 11 o'clock. Any other questions from today? All right. Once again, last announcement. No field today. Quiz today, this afternoon. We will text you when that quiz is available. Should be available right around between 12:30 and 1 o'clock. It is due tonight, and you'll see that on D2L. Any other questions? All right, gentlemen, have a good day and be safe.